So we are live now. I think we have to accept everyone.
All right.
You click on it, Paul-Etienne?
All right. Done.
Ya, yo creo que sí, yo creo que ya estoy, ¿eh? Sí.
Hello, good afternoon and good morning for the people who are in the US coast. Welcome to this webinar. So we are on time, start at 4, but we'll wait a bit, few, let's say, minutes that everyone join. Quite happy to be part of this webinar where we have the last data from our colleagues Violette in charge of communication. Will be more than 80 people this afternoon or morning again where you are. So for us it's very, very nice as we mainly use our network, so from LASEA and SAIT. So let's wait a bit. I can start to share my screen in order to be ready in a minute to start this webinar from LASEA in partnership with SAIT. Oh, I guess you can see my full screen now. Let's wait a bit. People are still coming. So here we go. So I propose to start this webinar organized by LASEA in partnership with SAIT, where we will present you the LS Lab system. That is, from our perspective, the right system for micromachining process development. So from our side, LASEA side, it will be more technical presentation, and we'll let the floor to SAIT to present case study, how in fact they use the LS Lab, and as a teasing also how they switch from LS Lab system to more to a machine still from LASEA. Before to start, I just want to introduce you the speaker. So for myself, my name is Guillaume, based in the subsidiary of LASEA in Bordeaux, in charge of business development with a strong focus on the APAC area. I am with Paul-Etienne.
Hello, everyone. I am Paul-Etienne Martin. I'm with LASEA since 20 years, and I am managing the site in charge of our BIM management modules and of our process development platforms that we will discover in this webinar. So today I will help my colleagues accepting first everyone and then gathering your questions, maybe answering them directly in the Q&A section, and dispatching them if necessary at the end of the presentation. So to ask your questions, please use the Q&A, Q&R, I don't know, button on top of your screen. All right.
Okay. Thank you, Paul-Etienne, for also this technical part of the webinar, because yes, at the end we'll have a Q&A session, and feel free to ask any question all over the presentation, and Paul Etienne will manage it. From SAIT, we have the pleasure to have with us Jorge and Iago. I let you the floor for a quick presentation.
Hi, can you hear me?
Yeah, we can hear you, Iago.
Yeah, so very nice to have you all here. Very nice for the people from LASEA to allow us to do with this joint seminar with them. We're happy. I'm Santiago Miguel Olaizola, Iago Olaizola. I am a group leader in laser precision manufacturing in SAIT in Spain.
Thank you, Iago and Jorge. If you can quickly introduce
Can you hear me?
Yes.
Can you hear me? And can you actually see me?
We cannot see you.
For some reason, the camera just backed out. Sorry about that.
Okay.
Yes, my name is Jorge Fantova, and I'm a researcher in the LPM group as well. And yeah, I'm a very technical guy, and working with kinds of femtosecond laser processing at the lab level. Thank you.
Okay, thank you, Iago. So the presentation will start with a quick introduction of LASEA. We will explain you why we developed the LS Lab and what is, at the end of the day, a LS Lab system. And then we'll let the floor to SAIT to explain what you can do with such a kind of system. And as you can see, it will be a picture of what you can do. And over the presentation, I will share also different aspects of how you can use the LS Lab. So quick introduction of the group LASEA. We are a Belgium company with a headquarter in Liège, Belgium. And we definitely develop, design, and produce a micro laser system, micro machining laser system with over a large portfolio today. And inside our group, we have 4 business units, means units that produce system, many machine. And we have also 2 subsidiary for sales and service, definitely to be close to our customer in the US, San Diego, and in Switzerland, in Biel. For the rest of the world, where we are also active, especially in Asia, we have a network of partners that are definitely a kind of extension of LASEA on this territory. So, as I mentioned, we developed and built definitely micro machining machine. I will start to quickly introduce our headquarter that is represented by the last platform that we developed here on the right of the screen, the NEO system. So in this facility, from my point of view and perspective, I'm always impressed when I go there, because we definitely push the boundary of what you can do in terms of micro machining, and definitely the DNA of the facility in Liège, it's to make very high precision machine. For some application, we are nearly talking about precision around plus minus 1 microns. That is crazy, with also a high level of automation. So, and these machines are mainly equipped with femtosecond laser. We have inside the group also Laser Cheval, maybe a company that you know. They were created a long time ago, 50 years ago, and today they are definitely on the shelf product, standard product, using either femtosecond laser or QCW, a nanosecond laser, for marking and engraving, but also welding application. Another site that we have a company in the group is Optech. Optech is a company that produced and developed a mask projection system also for micromachining application. So we use mainly excimer laser or TA laser inside this machine. But Optech, it's also, we used to say, our Formula One team, where we have the capability to make a unique system from scratch based on customer request that can turn after to standard product. And last but not least, the facility in France, represented definitely by Paul Etienne and myself today, where we developed and build optical modules for the group, but also LS Lab, the topic of today. And so when we talk about micro machining, this is an overview of all the application that we address with this machine. So it can be marking, engraving, texturing, thin film removal, it's a selective ablation, wire stripping, welding. One of our latest development is linked to turning application. And we have all this cutting and drilling application where, thanks to our precision module, we are able to have 0-degree taper. So for the French speaker, I definitely recommend a webinar that we did with one of our customer called Vulcam around 1 month ago or a bit more. It's available on YouTube, and we explain how we use this machine and also how we can combine different applications only with one machine. And so that's for the application. For the market, 3 main markets in that we target today with this system. It's luxury, electronic, and medtech. And all these markets are for us definitely support and key. For us, it's the research, let's call it market. It's all the university R&D center, but we put also from time to time the R&D department of companies where we deliver system and where today the LS Lab makes definitely the differentiation. So to answer this question, why we developed the LS Lab and what you can do with this system, I would like briefly to go back on our portfolio just to understand the process that ends up to the LS Lab portfolio. So we have, again, quite a standard product, definitely designed for production, where we can achieve various accuracy, productivity level, when we can treat a different size of material. We can, of course, connect it to external system to bring more automation. So here it's few examples of what we can do, but we have a large solution if you want to bring autonomy to your machine. So it can be, for example, roll to roll, like you can see at the top, a stacker, one of the last development from LASEA Cheval that give overnight shift autonomy or weekend autonomy to the machine. Or also we can integrate a robot arm to our system. So production machine, also very custom machine, as I mentioned, with Optech, that can definitely answer a proper environment from a customer. On top of behind that, we have all the module that we use in our system for beam management. And so this is also, we are able also to build a ready to be integrated system for production line or machine that we use inside LASEA group, but we can also sell outside the group. So this is the picture of our portfolio. And definitely, again, our machine are definitely designed for productivity, repeatability, quality, and to definitely meet high volume production. But it was more than or nearly 10 years ago. We had a customer called, let's say it was a lab called SAIT that we have today who come to us and say, we would like to have your system, but we don't care about productivity. What we seek, it's definitely knowledge. We would like to use your system to study the interaction between the beam and the material, to work on new material, to demonstrate laser processing, really on an early stage. But out of the production, we want all what you have behind your machine, means the repeatability, the quality and stability that you also offer with the system. And this is where we end up with the LS Lab platform. So definitely a solution made for engineer and scientist that is at the end with a good knowledge. You can have access to a lot of laser parameters. You have also access to different configuration. And the LS Lab is definitely built to also match the rest of our portfolio. It means that, for example, on some machine, we have a motorized beam expander that allow you to have different spot size or different tools, depends your point of view. It's a function that you find also in the LS Lab. Same for the precision module. If you want to develop or to test process that require 0 degree conicity, we can bring the LS process or precision module into this lab. And again, as it's something that is made for people who want to make some development, we think about the LS Lab upgradable and modular. And so today we end up with a port inside this product line, 3 different products. LS Lab Access, that is the definitely entry point of the LS Lab portfolio. And as you are part of this webinar, you have a kind of exclusivity today with the picture, because at the beginning we developed the LS Lab Access, a fully manual system. And since a week, our engineer just finalized the design and the integration of, let's say, motorized axes that are definitely, that doesn't bring precision, but just position, and definitely make the life of the user more easy instead to use this manual stage. But if you follow us, we'll make a communication soon around this upgrade of the LS Lab. And the main 2 that we have in our portfolio, it's an LS Lab Flex and the LS Lab Max. So the key difference is on the stages that you have. So at the end of the day, the sample that you can load into this this system. And so the Flex is equipped with stages XY of 150 by 150, and the Max, it's 300 by 300. And each time the DNA is to bring a high level of precision, but also stability, repeatability, that at the end, it's a mirror of what you can have later on a production machine. So definitely this tool is quite good for process development, prototyping. Here, what you can see, it's the open system. You will see just after on my presentation that we can put a safety enclosure to be compliant with the machine regulations, so the class 1 level. So that means you don't need any goggles to use this system. And also at the back, what you cannot see, it's the laser. So today we can propose a femtosecond laser from 6 watt to 40 watt as a standard with green, infrared, and UV. But if you have already a laser in your facility or in your lab, or if you want to use another laser like a picosecond laser or even a nano, we can definitely evaluate your request and answer your needs. Before to give the floor of to Sait to explain what you can do with this, I just want to share some picture of system that we sold all over the world. So here the focus, it's on university. So it's picture of a different university where we sold LS Lab. So you can see here the LS Lab with safety enclosure. So everything is covered. You have the light beacon, definitely like a machine. And so it's very convenient to use like this because you don't have to wear goggles and so on. So you can definitely be focused on process development. And today we have a lot of PhD students who made their thesis on such a kind of equipment. And the key element on that is that if there is a new request for the study, we can easily upgrade the system, or we can also add external module. I'm just thinking, for example, if you are looking for a top hat system or DOE or whatever, it's something that we can definitely integrate into this LS Lab. Another example here, it's in a R&D department where the customer starts with, at the beginning, one system dual wavelengths. So we just put also the sketch here to explain you what's happened and also what you can do in terms of upgrade. So he starts first with a dual wavelengths system. And he was not sure if there is some interest of to use the UV, and so we prepare everything at the beginning to be ready to upgrade it with UV units, and this is what we did over a year. So we use the system during 1 year, and then after a year, say, I would like to explore also the UV wavelengths. And as everything was already ready and the system is think to be upgraded, we add an extra station dedicated to UV to give the possibility to make development with these wavelengths. And today this customer is nearly close to production and think to move all the development to another machine. And finally, the example on research center where we deliver labs. You can see it's this time it's in clean room. So on the top, it's for photovoltaic development at IPVF, south of Paris. Where we did also a lot of communication with them. So if you follow us, you can easily understand what we can do with the LS Lab. And below in the Semicon R&D environment, where they do a lot of stuff. And one of the research center that we address, it's SAIT. And so, Jorge, I let you the floor to explain us what you're doing with the LS Lab.
Okay, thank you, Guillaume. Let me share my screen. Second. Can you all see the presentation?
Yes, in full screen. Yeah.
Okay. Well, welcome everybody. Yeah, we would like to tell you a little bit about what you can do with the LS Lab. As Guillaume mentioned, we were one of the first to receive such a machine, and well, we have quite a lot of experience with it. This is the introduction. I mean, the presentation outline that we will follow. And now, first, Diago will give you some insight about who we are and our placement.
Yeah. Thank you, Jorge. Yeah. So thank you for your time. I just wanted to a framework. How do we approach these systems? Because I think it's important to give you a framework of our background, and therefore you can actually know our interests or how we approach LASEA for this. So basically, THEID has a very strong background in materials and microfabrication, so clean room technologies. And at some point, we wanted to do small things for micro things with lasers and to have this knowledge. And this has actually picked up quite strongly, and now we are a laser focus group. Instead of having a microfabrication group, we're a laser focus group. And we have turned into a group that, as you can read there in the slide, we use ultrafast lasers to develop manufacturing processes with high precision for industrial applications. We are a research center that is very focused in industrial customers. So for when we first approached LASEA, said we want to test your equipment, we want to test ultrafast laser equipment, but we know with a limited investment, let's call it this way, okay? How limited? It's always more limited than they wanted and a bit more less limited than we want, but we had an agreement and we purchased the LS Lab for testing multiple things to be as wide as possible in applications and everything. So yeah, we as Guillaume told, we didn't care about productivity. We care more about flexibility and being able to do different things. So we basically started like that. Probably it was 7-8 years ago. I cannot even remember, which time flies. And we basically wanted to use this cold ablation process for different surface processing, texturing, engraving, and some bulk processing and transparent materials. Jorge, so if you can switch. So we have all the supplementary technologies, all the thin film growth, photolithography, PVDs, CVDs, all these things we had already in-house on all the microscopy and non-contact optical peripherometry. And of course, you can see there are some photographs of our premises. If someone is interested in seeing in live, just contact Jorge or contact me at the end of this seminar. We are very, very happy to have visitors in our premises. You can see there we have on the left some amplitude system laser, which we use for even lower TRLs than laser can provide. So we can have a very strange setups with different motors and different access, then we can do it ourselves. Of course, if we want some more stability, something more professional, the right thing is to go for a LS Lab or something similar in the market. In our case, it was LS Lab because it produces a robust way to process materials, thin films, and surfaces. And just to end this framework, I would say that now we use after 6 years, after a couple of years ago, we purchased a LS4 lab, an LS4 machine, industrial grade, full industrial grade machine. You can see it there. Both of them are in the clean room. Okay, so we can do laser process plus microfabrication material growth within the same lab, basically. And it's been a great, I think it's been a successful story in the sense that we got the LS lab quite, I would say, quite inexpensively as a first investment, and we could test it and we could see that it worked basically. And then our clients got more interested and they wanted more parts, or they wanted larger parts, or they wanted some kind of industrial projects development, and we use for that the industrial grade LS4 machine. Okay, and it's a great way to get into the technology with control risk in this sense of view. So at the moment, you can see that we're using the LS Lab. Still, we are using it when we need proof of concept, when we want to fast arrangement of the optics of the stages or whatever. And then we use the LS4 more for pre-production and validation activities. All in all, it's very nice because as the optics are compatible, it's not direct. It's never direct I think in optics to go from one setup to the other one, but it's not painful. That's how I can say it's not painful. So it's quite easy to get one proof of concept in the LS lab and then implement it in the LS4 machine for industrial validation. Okay, I'm going now to let you know, to give word to Jorge, so he can actually describe how are we using the LS Lab in our premises. So Jorge, you have the word, you have the floor.
Yeah, thank you, Iago. So first, I would like to talk about how we implemented the LS Lab at our facilities here in San Sebastian. Yeah, in this slide, I'm showing the LS Lab station implemented in, as Iago mentioned, in our clean room facilities. It is mounted on a granite platform and comprises several modules, which are pointed here. And as we see here in this diagram, we have first both a power and a beam size management module that is motorized with beam expansions of 2 to 8. Then we have afterwards a polarization module, which can be automated. In this case, it was manual. And lastly, a processing module which is based on a Galvo scanner with a 100 millimeter FT lens for push delivery and an XYZ stage precision system for sample positioning. So, and in this case, in this setup, we are using an amplitude Satsuma HP femtosecond laser source with a wavelength of 1030 nanometers and some burst capabilities in the megahertz. So, yeah, it was also mentioned by Guillaume, right? Being an open system, the LS Lab is really compatible with other optomechanical setups that you don't have to, let's say, limit one laser source to one setup, right? So to show you this, we have here a top-down view of part of our optical table, where we have here the laser source, and this is the main path that the laser follows towards the LS Lab station. And we have this Gaussian beam. But through the introduction of different optics, we can also deflect the beam, since it's open, to other setups, or to other experimental or proof of concept setups, which, as the ones I briefly point here, we had up to 3 different optical setups directed to a engraving station for some beam shaping tests that you see here. So really, the main limiter is the size of your optical table, which never seems to be enough, as you are in research, you know. So moving on to the 2 case studies that we have prepared for today. The The first case study is about the microstructuring of injection molds with femtosecond lasers. The results are presented in the context of the FemtoLens European project, which was really focused on the production of freeform lenses for tailored lighting applications. And from the different partners, in our case, the challenge here was to define a laser process strategy to accurately replicate the features of the mold that we want to fabricate. To achieve this, we followed a 2.5D laser micromachining strategy, which I will briefly review for those that are not familiar with it. Basically, we start from a target steel design that we point here. And what you have to do in order to do the micromachining is slice, let's say, from top to bottom, this 3D structure for the laser engraving. And each layer represents one laser pass, which we are doing ablation. And you have to know, in order to achieve a very smooth and accurate engraving, first, you have to tune the laser parameters, such as the spot size, the power, etc., to achieve a homogeneous engraving of a single layer. And then also you have to optimize the separation in Z between each of the layers, where a bigger separation would mean a higher throughput, but less resolution. And generally, we are more interested in the resolution and in having a finer feature. So we tend to go to have as small as possible gap between the layers. To give you an idea, between 0.5 and 1 micrometer. And it is worth noting that both the slicing of the structures and also the modulation of the different parameters can be done through the LSLab platform and the Kyla software that comes with it. So it's pretty handy. So yeah, jumping straight into the details, just to show some of the results. After optimization of the laser conditions, we fabricated several lenses, in this case on a stainless steel substrate. To give you an idea, here's the target steel design of one, let's say, Fresnel-like lens. We can also see here the final lens on a macro picture, which is of a 2 centimeter diameter. And on the right here, you see the topographic images of this engraving. And the false color means the difference in height. And you can see here focused on the center of the engraving. And you see that you can see that there is, to give you an idea, a peak to valley height of around 36 micrometer and a periodicity in these rings of 130 micrometers. So in this case, we achieved close replication to the intended lens geometry. So this was nice. And just to give you another example, in this case, it was another multifaceted. This one was a multifaceted lens. And here the scale was rather, for us, it's rather different. Instead of in the tens of micrometers, we are in the hundreds of micrometers, both in, let's say, in the height and in the spacing and XY movement. So this is just to show that the engraving strategy can be applied to replicate a variety of freeform structures. Furthermore, in some cases, we also perform something that is very hot right now, laser polishing through the femtosecond lasers. So after doing the micromachining of the lens, we did a kind of laser profiling, just following the contour of the lens. And in this case, by using the megahertz burst, we were able to polish the lenses. You can see here some of the results. And basically, we were able to achieve in this case a reduction of around 40% in the surface roughness, as you see here. Yeah, and just to give you an idea of the second use case, yeah. In this one, one of the different, let's say, operations you can do with the LSLab. The second is about the selective decoating and texturing of thin films. And we want to show how by using this ultra-short laser technology, we can do it we can, let's say, have a very precise and selective decoating in a very straightforward manner. And this, well, of course, that has applications in the industries such as luxury, lighting, and microelectronics. So this is the diagram to show you a little bit what we mean by this. Essentially, when we're working with a multi-layer stacks, we're able to selectively decode or ablate the different layers and in different patterns. And depending on the use case, one might not only want to decode, but instead of decoding, you want to texture the actual layer without affecting the ones that are below. And you can also achieve this with this technology. And the challenges here is basically to have a high enough engraving accuracy. We say in the order of tens of nanometers, and also to have it be homogeneous across the whole surface area and not have any damage to the layers that are below. So I will show some examples. In this first one, we show how on the left, by tuning the pulse overlap, we are doing a gradual, we achieve gradual light transmission by decoding step by step, let's say the chromium coating on a glass substrate. And also you can go like to finer structures by tuning the power and the beam size. And we have like holes of 50 micrometers or lines of 10 micrometers or lower. In this case was a much thicker aluminum coating. Another example is for us is very interesting, is that you can, talking about the selectivity of the process, we can selectively coat a multi-layer metallic stack. In this case, it was for a metallic for decorative purposes for the industry. We see here on the left a diagram of the look of the coating from the top and the structure, 3-layer structure of the coating. And through this electronic microscope, in this case, it was for a metallic for decorative purposes for the industry. We see here on the left a diagram of the look of the coating from the top and the structure, 3-layer structure of the coating. And through this electronic microscopy analysis and the imaging and the elemental analysis by EDX, in this case, we achieve to decode only the topmost layer, leaving the palladium and gold layers unaffected. But you can go, you can have a larger removal, let's say. In this case, we were able to remove the whole coating stack of 3 layers, starting from gold, and on the bottom was, let's say, a nickel substrate. And in this case, you see that the gold and the chromium has been eliminated, but and therefore the nickel resurfaces or is revealed by the ablation. Just giving off this bluish color. In this process, we achieved a precision of around 50 nanometers in this context. And lastly, let's say linking with what Yago was mentioned, right, about that it is very interesting to combine both the capabilities of thin film deposition and also laser decoating or texturing. In FATE, we can generate metal and oxide coatings with thicknesses of around from 20 nanometers to a few micrometers, which can provide not only this very beautiful coloring that you see here, but also like tune appropriately the optical properties of the surface of the substrate. And furthermore, by combining these two, you can, for example, laser texture the substrate before the coating to provide some functionalization, like for example, to control wettability or to have some anti-counterfeiting features. To have for some applications. In particular, these samples that you see here were laser textured, and then we coated them with some PVD for decorative purposes. Just to close the presentation, just to remind what we have seen is that in the beginning, the LS lab is, well, it was a very great addition to the lab and is still being used. But as, let's say, the technology moves forward and more industries are thinking about integrating these technologies into their production lines, we have seen that indeed it would be very beneficial to give them more, let's say, reliability and have it more industry integrated, have it be more easy. So that is why we purchased the LS4, and we think systems like this would be very beneficial for industry, but not only industry, but research centers such as the ones that we are. To get more customers due to the higher throughput and productivity and the advanced process monitoring, or the possibility to process by complex parts that you can do with this kind of system. So yeah, this was all that we wanted to talk to you about today, and we would be glad to answer your questions later. Thank you.
Thank you very much, Jorge and Iago, for this very nice presentation of how to use the LS Lab and what can bring the LS Lab. And definitely, I just want you to join the conclusion of Jorge, where at the beginning they get this request. I don't want this machine, but want the LS Lab. But today turn that the request is the opposite, so they develop everything. They have the possibility to develop stuff on the LS Lab and then to move it into the machine. So we are perfectly on time. Thank you very much for your attention. Here you can find again our contacts. So if you have any question, if you want to know more about SAGE, feel free to contact Iago, Jorge. For LASEA, Paul Etienne, or myself, it's very nice, so feel free. And so now we can go through a Q&A session. If there is question.
I don't see questions, but don't hesitate to ask. So with the Q&A button on top of your screen, feel free. Maybe to start the session, Jorge, what type of materials do you process the most? Do you work on many types of material, or?
With the LS Lab or in general?
Yes, well, LS Lab
Yes.
and LS4, yeah.
Yes, I mean, traditionally used because they are the most used in the industry. Many different kinds of metals, stainless steel, chromium, copper, and plastics like polycarbonate or PMMA, whichever is more interesting for the industry. Or like, for example, a lot of glasses that we can process, like silica or silicate, the typical ones, yeah. Typical ones, but the good thing about the femtosecond laser is that you can virtually process any material, although some are more tricky than others, but yeah.
All right, thank you. Have one
let me add a bit about that, because I would say that probably most of the processes that are metals ones. So I would say that metals are, but also lately there are some metal oxide. We're going into the chemical world as well, and we're doing something within batteries or with catalytic materials, or this kind of really let's call it flamboyant materials, where you have copper oxide, you have iron oxide, or you have this kind silver oxide and these kind of things, where you can do lots of things in the energy world nowadays, and people who are in these areas, I think there is quite a good room for research, and the LS Lab can be a very nice tool for research these new materials, or these different materials.
Thank you, Iago. One question on the SHG, so meaning can we convert the fundamental wavelengths to green, or probably UV2? So the answer is yes, as Guillaume presented first. Well, we can have an LS Lab which is dual wavelengths, so both wavelengths will go through the same beam path in one station. So you simply have to combine the two outputs of the laser. on the optical table, and then you will be able to switch with on the software from one wavelength to the other. For the UV, we recommend having a separate beam path, so second station, because three wavelengths beam paths are possible, but not very well, they do not withstand a high power, so the lifetime could be reduced. So we recommend using a specific beam path for the UV wavelengths. Another question, probably for Jorge or Iago, how do you approach parameter tuning? How long did it take to find the right process parameters for the applications you have showed?
Yeah, it really depends on the material we are talking about. For the steel, for example, since we are quite used to it, I would say like to adapt from one process to another would be like a matter of 2 weeks or something like that. For developing a new process on a new material, like for example, recently this was not done on the LS lab, but rather on the LS4, just because we had the green wavelength. We are doing some 2.5D micromachine on diamond, on single crystal diamond, and yeah, for more tricky materials like these ones, where you have to, let's say, you have to be concerned with other effects, graphitization. Maybe you can do it in a month, like to have a proper, let's say, as a small let's say the highest resolution and the lowest surface roughness that you can get with the, let's say, the system that you have for more tricky ones. But yeah, just to give you a rough idea.
And how do you proceed? For example, do you do matrices of parameters and then identify the right roughness and so on, and then apply to the right geometry, or?
Yes. Generally, starting from, I mean, if you go if you have a lot of time, maybe it all depends on the time, right? But for example, you have a lot of time, maybe you can start, and it's a brand new material. Maybe you want to align and see exactly how the material is behaving to one line, then you jump to an array of lines. But I mean, generally, yes, we are doing matrices of matrices of process parameters like power and pulse overlap is the main one. If we have a very symmetrical beam, we can use symmetrical overlap in the two directions, and we do matrices like power and speed. In some cases, maybe it is like good to have some, let's say, first processing, let's say, to prepare the surface, to make it rougher, let's say, so you have later a more consistent process. It's a bit counterintuitive, but yes, there is a lot of steps to it if you really want to go very, very fine. And yeah, another parameter is to really find the right, for example, the hatching, right? You are doing several layers, and you are not only moving them in Z, but maybe you also have to rotate the hatching in order to have it be very, very homogeneous. And yeah. There are plenty of parameters that you can tweak. Indeed, it is very handy to have automated control of all of them, like you can have in the LS lab. Yeah.
All right, thank you. Another question: what energy per pulse and repetition rates were used for the two applications you described?
Okay, so they were very, very, very different. So on the first one, I would assume I was not myself. I was not in this. I don't know the whole technical details, but I know that, for example, we are using with the LS lab that we have. We are typically always working with the 500 kilohertz, which is the maximum, let's say, single pulse frequency that we have. You know, you have a faster process, right? And I think in terms of pulse energies, we are moving in the range of 2 to 4 microjoules, And yeah, something like that. And in the other applications, maybe you have to go much lower power. For example, for the decoding, maybe we're talking about 0.25, 0.5 microjoules, depending on the case and on the thickness of the layer, right? Because for the ones that you have to decode 15 nanometers, it's very, very different to few micrometers that you have. Yeah. So really depends.
Pretty low energy per pulse, but high repetition rate. It's typically the case for surface processing where you don't need a lot of energy. However, if you want to cut or drill or go deeper in the material, then you usually need more energy and lower repetition rates. All right. Is there a new question?
Still have 5 minutes in front of us, so maybe a last one, and then if there is one.
No, I don't see any question. Feel free.
Yeah, just to jump on the question of rate energy. So as I mentioned, so we can combine from 6 watt till 40 watt. We can go up to that. The question afterward is, does it make sense if you want to work on a small surface? Energy, we can definitely go quite high. When we use, for example, the 40 watt system, we have 400 microjoule energy outside the laser, and we can turn it also in a second harmonic to have 200 microjoule and nearly 100 in UV, something like that. So yeah, again, the system it's developed like our machines to be robust in front of this laser. And back to SAIT, they have laser, Satsuma laser from Amplitude that is a 20 watt for 10 microjoules, something like that, where they can also play with energy and power easily.
I have a new question. How long it takes to process and polish a typical lens mold as you described? Okay.
Yes. Yes. It really depends on the power that you have and the repetition rate. Yeah, as Diego mentioned, we are not so concerned about productivity in the beginning. We want the flexibility. So in this case, for the engravings that we did, for example, the one that I showed, it was like a 40 micrometer depth, and it had like a diameter of 2 centimeters. I think it was around 2 hours that it took for it to complete, using the, let's say, the optimized, using the let's say the parameters, the 500 kilohertz repetition rate. Of course, if you have higher power, this means higher power and higher repetition rate, you can go faster with the marking speed. So yeah, it really depends on the ones you have. For example, the laser shows the Satsuma HP that we use had a 10 watt power, but for example, the Satsuma X that we have in the other setup, it has 50. So it really depends on the machine that you have. Yeah, but for us, it was definitely enough.
And you think you would have room to improve the process speed by increasing the power? Did the material with
Definitely.
Yeah. Let me follow on that, because I mean the time it takes is actually depends more on the depth that you want to engrave. So as we have a laser that it's more used or more thought to for surface processing. Anything that goes far below the surface, it's time consuming for us. Okay, so for some, for example, for some molds that are up to 2 millimeters in depth, it can be 1 day. So if we are going to engrave 2 millimeters, sometimes it's better for us to do a preform with mechanical means and then do the last 30 or 40 micrometers with the laser. That's the way we normally try to do it. Because if we want to do it all with a laser, in our case, with the setup we are dealing with, that it's more for the surface, then it gets very, it can be done. It definitely can be done, and it's okay for research and development. It's more than okay. It's brilliant, but then it's not. It hasn't got throughput because we haven't thought our lab for throughput. Definitely, it depends on the depth of what you want to engrave. That's the main thing. That can be from minutes, from 20 minutes down to hours, up to hours. And the also the polish process is quite fast, I would say. The polish process, it's some minutes or seconds, even depending on the area, but that is much faster.
Okay. So we are at the end of this webinar. Thank you very much for your participation. The session was recorded, and so if you are interested to see it again, it will be available, I think, on our YouTube channel. If you have any question, again, feel free to contact us again, our contact here. And if you want to share also this webinar, feel free. Thank you again for your time and your attention, and have a good day.
Yeah,
Thank
thank
you.
you.
Bye-bye.
Have a good day.
Bye-bye.
Bye-bye.
Bye-bye.